So we're starting today with kind of the conclusion of chapter 11. And in this chapter 11 conclusion, we're really only talking about three different groups of materials. The first we're actually pretty commonly aware of and familiar with, and that is nitrates and nitrites. The differences between nitrates and nitrites are in the formula of the ion that is being used. Nitrites have the formula NO2-1. Nitrates have the formula NO3-1. And so what we would see in these are a combination of sodium with one of these, or potassium with one of these. Now, both of these are common oxidizers. Where we see them used most often, at least in terms of common usage, is as preservatives. We add it to meat products as curing salts. These are the primary things that allow jerky and summer sausage, bacon, and those other kinds of cured meats to have a longer, more stable shelf life than what they would have on their own just as processed meat products. And the oxidizer is there for a couple of reasons. I mean, it does provide some flavor. It does provide some of that cured kind of taste that you're used to when you have a bacon or a sausage or something along those lines. But the primary reason there is, as an oxidizing agent, it's going to provide some power against bacteria invasion. Now, there are some downsides to this. Nitrites have been linked to the formation of N-nitrosamines in your stomach. Those nitrosamines are carcinogenic in nature. So the potential development of a chronic effect related to the ingesting of nitrites is a possibility. These generally tend to develop over long periods of time with high degrees of exposure. We also know that sodium nitrite and nitrate, if inhaled or ingested in a high enough concentration, can lead to methemoglobinemia, which, if that sounds familiar, we talked about that in our toxins unit. That is one of the hemoglobin inhibitors. So it can affect your oxygen transport if we're in high enough concentrations. Good thing for us is that rarely are those kinds of exposures going to be coming from something that we ate. Concentration of sodium nitrate and nitrite in cured meat products is usually not enough to cause that level of hazard. Usually we come from directly ingesting the salt itself, which is why in curing agents, you will often see that these salts are dyed pink, not only to give a characteristic color that we associate. Pink salt gives meats like bacon a pinker kind of complexion that prevents oxidation, prevents that kind of discoloration that comes with meat sitting out for a while. But also so that you don't accidentally mistake it for a sodium chloride or another kind of normal salt product. Now, nitrite, because of that lack of a third oxygen, nitrites have the ability to act either as oxidizing agents or reducing agents. As a nitrite, again, nitrite being NO2 negative 1, what we have here is the nitrogen in a positive 3 state. So in the positive 3 state, it has the ability, we look at nitrogen on the periodic table, and we see that nitrogen in compounds, nitrogen as an ion standalone, would rather be negative 3 than positive 3. So as an oxidizing agent, it can continue to work its way down to lower oxidation states, ones that are less positive and more negative. That's its natural tendency as a non-metal. But because the nitrate ion exists, NO3 minus, and that nitrogen has a positive 5 state, it is possible that the nitrite ion can also act as a reducing agent. Get oxidized further from the positive 3 to the positive 5. So nitrite ions are kind of in the middle. And because of their in the middleness, their in the middle state, they tend to have more reactivity because they're a little bit more flexible in terms of the kinds of reactions that they can do. Put them in with a good oxidizer, and they'll go to nitrate. Put them in with a good reducer, and they'll deform into nitrogen monoxide, which is a positive 2, or nitrogen gas, which has no charge, or even a negative 3 charge if we get enough electrons to it. Nitrites overall are generally stable, but if we heat them high enough and consistently enough, they will decompose. Nitrates, on the other hand, because they have no other place to go, and we're talking about NO3 negative 1 with nitrogen in the positive 5 state. If I look at the periodic table, I can see that nitrogen has 5 valence electrons. It's already lost all 5 of those electrons in that positive 5 state. So it has no more electrons to lose. It can't be oxidized any further. So its potential as a reducing agent is gone. All that is left is its oxidizing potential. Now, when it oxidizes, there are lots of different compounds that it can make. It can make nitric oxide, it can make nitrogen dioxide, it can make ammonia. So in the presence of acid, we can get lots of different compounds. All of those in lower oxidation states than the nitrate is in currently. If we have non-alkali metal nitrates, so things like magnesium nitrate or silver nitrate, those will always decompose into the metallic oxide, nitrogen dioxide, and oxygen. Those equations aren't balanced, but we get the idea. In their decomposition, we are going to see transformation of that nitrogen and the transformation of that oxygen. Oxygen is going to give electrons away to the nitrogen as it decomposes. And these obviously pose problems of their own in decomposition because we have nitrogen dioxide, we know is a heavy-duty oxidizer because of that unpaired electron on it. And there's a toxic gas, we talked about it in chapter 10. And we get the formation of oxygen, which we know can fuel fires by its presence as well. Now, as far as regulations for nitrites and nitrates in food products, this is where the Food and Drug Administration, the FDA, comes in. There are maximum concentrations for these compounds. In particular, we're usually talking about the sodium compounds, sodium nitrate, sodium nitrite. There are maximum concentrations allowed in foods. On the ingredients list, it has to carry a warning saying this is what's in it, here's how much of it there is, here's how to use it, keep it away from kids. Now, just on an interesting side note, it's been a couple of years since this movement kind of took off, but you probably noticed that there's kind of a natural food movement that's been kind of going through the past few years. Let's get rid of artificial vanilla. Let's get rid of artificial colors and flavors. Let's take nitrates and nitrites out of our processed meats. And all that sounds great on the surface. You gotta read the labels pretty close. For preserved meats, ones that say that they aren't made with, that there are no nitrates added, read the ingredients. If they've added celery juice to it, celery juice is a natural source of sodium nitrate and sodium nitrite. They're just substituting one thing for the other. No, they're not adding pink salt in the processing like they used to. They're still adding nitrates and nitrites to it, which is good for us on the consumer side, because that means it still tastes the way it's supposed to taste. It's going to still have that cured meat flavor. But if that is something that you are concerned with, or you know people who are in that kind of realm, that's how they live their lives, that's how they view the world, just make sure that they're aware of that. Because if your goal is to get away from pink salt, yes, you've technically gotten away from it. But that's really not the thing that you should be worrying about. You're really worried about additives. Celery juice is an additive, the natural one, but it has the same chemicals in it as the thing that you're trying to avoid. So just a little side note there. All right, the next to last thing that we want to look at are persulfate compounds. Persulfates or peroxydisulfates. Where we see these are primarily in the computer industry. It is a processing agent for kind of cleaning the silicon wafers right before they are turned into processing chips. And persulfate ions are responsible for that. Now, there are two different ions that carry this label as persulfates. You can either see it as SO5 -2. This is where the peroxy kind of piece comes in. You can also see it as S2O8 -2, kind of like what would happen if two sulfates bonded together. Either way that you look at it, this is the compound that you have to be aware of. And it is a particularly powerful oxidizer because what you have here is you end up having sulfur in the positive 6 state. And we've already talked about when we have high oxidation state kinds of compounds, we know that they're going to be especially reactive. So we just talked about +5s with nitrate. We talked about +6s in chromium, and now here in sulfur, we talked about +7s on Wednesday with manganese. So this is pretty powerful stuff. It's going to be highly reactive. So the last thing that we want to get into in this oxidizers unit is probably the most common consumer product that uses oxidation, and that is matches. Now, when it comes to matches, we know that there are two types of matches. There are the strike anywhere matches. These are ones where we see a combination of fuel and oxidizer on the match head together. And all you need is some kind of abrasive surface to cause enough friction to get the reaction to start going. That's why they're called strike anywhere matches. You have any kind of rough surface, that's all it needs to get the reaction going. Safety matches, on the other hand, are the ones that we're more familiar with. These are the ones that usually have a striker on the side of the box or a striker on the back side of the matchbook. Inside of that striker, that prepared surface, we usually have a combination of red phosphorus, which is going to act as primarily your fuel, and powdered glass to give that roughness, that friction, to provide enough energy to kickstart the reaction. Now, In terms of our flame triangle, remember we brought up this concept when we first introduced the idea of combustion. We looked at our flame triangle here. We can see that there are 3 legs on the triangle: oxygen, fuel, and heat. In a strike anywhere match, the oxygen source, the oxidizer, is coming in the form of the lead peroxide. Lead peroxide, when it is struck against a rough surface, is going to initiate the decomposition of that lead peroxide and turn it into pure oxygen gas. So that combination of the oxygen coming off of the match head plus the oxygen in the atmosphere around it is going to be enough to get the reaction, enough oxidizer to go. As far as fuel is concerned, you've got in the tip of that match, you've got the tetraphosphorus trisulfide, you've got sulfur here, which will act as kind of a actuator. Once that lead oxide starts to decompose, it'll start to immediately burn the sulfur that's near it. You also have the wax that's holding all of it onto the matchstick, and you have the wood of the matchstick itself. The heat is going to come from the reaction of the fuel and the oxidizer to each other, plus the frictional force coming from just rubbing that against something. For safety matches, we have the oxidizer and the fuel both together on the match head itself. Red phosphorus and powdered glass are on the striker. And so what's happening is as you're striking that red phosphorus, that match head against that phosphorus strip, it's starting to initiate the reaction between the phosphorus and the potassium chlorate. I already talked about potassium chlorate. It's a pretty good oxidizer. So it's generating a good chunk of oxygen right away as it is being struck. With that heat from the friction, from the early combustion of the phosphorus, we now have enough to continue that decomposition of the chlorate and light the antimony trisulfide compound that is also in the match head to get the reaction fully going, get the fire lit, and sustain it for as long as we have fuel. So that is all for chapter 11. I took us a while to get through everything, but there are so many reactions and so many common products that use oxidizers in some way or another that it's really hard, even in these 4 days, to do full justice to everything that you might see or might encounter with that. That being said, any questions that you have for me before we put this one to rest?